Today I'll be talking about effective straggler mitigation in the context of interactive jobs. Interactive jobs are increasingly becoming quite common and popular in today's data analytics clusters. These are more exploratory and experimental kind of jobs that are fired by data analysts on small selected samples of data. And because of the fact that there is a person waiting and it's interactive, low latency is kind of crucial. And since the job itself operates on carefully selected samples, these jobs tend to be fairly small in size. For example, in Facebook's Hadoop cluster, nearly 90% of the jobs had fewer than 50 tasks in them. These interactive jobs are pretty sensitive to stragglers. Stragglers are tasks that are much slower than the other tasks in the job. And because of the sensitivity of these jobs to stragglers and the importance of these interactive jobs in itself, in general, straggler mitigation has received considerable attention. And the techniques that have been developed could be put into two broad categories. One is blacklisting, where periodic tests are done to find machines that are faulty, like for example with bad disks, and they're eliminated for scheduling. The other category that we call speculation addresses the non-deterministic or the runtime stragglers. These two techniques are things I've mentioned here because they are in deployment at Facebook and Bing. And well, there are a whole bunch of other techniques as well. Despite these mitigation techniques, what we see is that stragglers still occur in these small interactive jobs. For example, in the Facebook cluster with the late technique in effect, the slowest task in the job still runs nearly 8 times slower than the median task of that job. The numbers are similar, albeit a little lower for monthly. And note that here we're not measuring task duration per se, but task duration normalized to the input size as such. So data skew and things like that are already excluded here. These techniques, however, work well for large jobs, for the large production jobs. The question is, why is that? Let's see what these techniques actually do at a high level. There are two steps that they perform. One is observe, which is to measure the relative progress rates of tasks and kind of build a model for things that are normal in this job and things that aren't. And then go ahead and launch speculative copies for those tasks that are not normal, like stragglers. Now, this technique seems fine, but why doesn't this work for small jobs, the interactive ones we're interested in? For two fundamental properties of these jobs. One, as I mentioned earlier, they consist of just a few tasks. Second, since they have only a few tasks, there are enough slots in the cluster to run all of them simultaneously. Since they consist of just a few tasks, it just becomes statistically harder to build a model and have accurate prediction for these stragglers. Second, since they run all their tasks simultaneously, just observing and building a model itself constitutes a sizable fraction of the job's duration. Hence, for these reasons, this idea of observe and speculate, this reactive technique of observe and speculate, is not particularly suited to address stragglers in these jobs. In contrast, what we propose is a simple idea that proactively launches clones, multiple clones of a job, just as they're submitted. We pick the result from the earliest clone. Of course, this probabilistically mitigates the effects of stragglers. And this simple technique, of course, eschews any necessity for observing and building a model or any sort of causal analysis. The natural question, of course, this technique sounds simple, but the natural question, of course, is this really feasible given that we now require so much extra resources? In 3 production clusters that we've seen, from Facebook, Bing, and Yahoo, there is a strong heavy-tail distribution in the job sizes. This graph on the y-axis plots the fraction of jobs to the total number of cluster cycles that these jobs consume. clearly, most of the jobs, the smallest fraction of the jobs that we are interested in use only a small fraction of the overall resources in the cluster. For this reason, there definitely is potential to clone most of these small jobs without blowing up the cluster. So what we've seen is that interactive jobs are important and small, and that they're hardest for straggler mitigation techniques. However, the heavy-tailed distribution means that we could actually clone these things and then avoid these pitfalls that are there with these traditional mitigation techniques. Cloning now, however, creates multiple copies for every task. And so one of the main challenge in doing so is to avoid I/O contention, which is specifically put that every clone should get its own individual copy of the data to read from. This data is either something that's read from the file system, the distributed file system, which we call as the input data, which is typically replicated, or intermediate data that is passed across between the tasks in a job. Intermediate data, of course, is not replicated at all. There is only one copy, and this is to avoid overheads. So to solve this challenge of avoiding I/O contention in this cloning, let's pick the harder case that we have, which is the intermediate data of the jobs, and we came up with a straw man that tries to avoid this problem. Say a job comes in, 2 tasks here, T1 and T2. We just create 2 copies or multiple copies or clones of this job and just pick the earliest. This technique, of course, is also appealing because it's simple, it's easy to implement, and it just directly extends to any framework. The trouble, however, is the number of clones that it requires. This graph on the y-axis plots the probability, the analytically calculated probability of the straggler in a job with the straw man to the number of clones it requires. And clearly, we require a lot of clones, much more than 3, for us to have any sizable, acceptable guarantees in terms of the probability of the straggler in the job. And of course, this 3 number is important because it's close to the replication factor that's usually employed in these systems. And just simply increasing the replication of all these files isn't quite an option. As some of you would have guessed, the main problem with this straw man that we had was the point that we were looking at a set of tasks together and picking a winner among a group of them. A natural alternative to this is to go fine-grained, which we call task-level cloning, where, say, the same example, 2 jobs come in, P1, the job comes in with 2 tasks. We now create, clones of each of the tasks, clone groups in each of the tasks, and pick the earliest within the clone group of every task here. This fine-grained thing fixes the problem in terms of the number of clones we want. The graph on the left shows the one that was there for the straw man earlier. The graph on the right plots the probability of the straggler in the job with respect to the number of clones for task-level cloning that we have. And clearly, we see that with 3 clones are plenty here, are sufficient. So we solved this problem of input data contention with this task-level cloning. However, the trouble here happens to be that now we push the problem to intermediate data contention. Intermediate data is, of course, those that are passed by the upstream task and are read by the downstream tasks. Like in the same example as before. So there are 2 tasks. So this is the upstream phase. There are 2 tasks that come in, and we had like clones of both these tasks. And at some point, of course, one of the clones has succeeded at being the earliest. And at this point, say we have downstream tasks or clones to schedule. Since we have only one copy of the intermediate output now, how do we actually do this management in terms of how the data is read by these downstream clones? Now, there could be 2 extreme options here. One of them is, of course, that we could assign the earliest copy that is there to both these downstream clones, in which case both D1 and D2 read from the upstream clone that is finished. And this is great, but for the fact that the intermediate data transfer now takes longer. Since this causes extra contention in reading the intermediate data, we call this a contention cloning. If you swing all the way to the other extreme in terms of the design space, the option is to assign exclusive copies. Or in this case, say, when we have one of the upstream clones that have finished, we assign that to one of the downstream clones and tell that to read from the upstream clone. And then the other one waits for the other two upstream clones to finish as well before reading its data. But then here by design, we've actually disadvantaged one of the clones. However, since this avoids contention, we call it contention avoidance cloning. But surely, since we've disadvantaged one of the clones, the job is just much more vulnerable to stragglers. Or in other words, the benefit of cloning is much reduced anyway. So what we've seen in terms of avoiding intermediate data contention is those two extremes where we had contention avoidance cloning and contention cloning. One of them, of course, avoided contention, but made the job much more vulnerable to stragglers. The other one, of course, did not really make any of the tasks disadvantaged, but cause contention in reading the intermediate data. Analytical and experimental results show that with CAC, the vulnerability to stragglers in the job increases by over 10% in the job. And in the other case with CC, the intermediate data transfer takes 2x or 50% longer. So the question now is how do we minimize contention, without actually getting the downstream tasks to straggle? The key insight in our solution is to distinguish intrinsic, perhaps small variations in task completions and task durations from the stragglers. If we can do this, then what we can do is to have a small delay to get the exclusive copy of the output to see if the upstream tasks finish before we go ahead and contend for the available copy that is there. In our solution that we call delay assignment, we set this delay using a probabilistic model for task durations and the read bandwidths with and without contention. And we try to balance out the two in terms of which one we should pick. And this delay is, of course, updated automatically and periodically based on samples that we get for both task durations and the read bandwidth. So putting it together, what we have is a solution called Dolly. This is for cloning jobs, and this is after the first sheep that was cloned. This performs task-level cloning of jobs. It uses delay assignment to manage to avoid contention in intermediate data, and then it works within a small resource cloning budget. That is, jobs are cloned only if there is sufficient budget available. Let's see how well Dolly actually performs. The baseline that we use is, of course, the two straggler mitigation strategies that I had mentioned earlier in the talk that I said were in deployment. We also use a blacklisting technique to weed out all the problematic machines. And we set a cloning budget of 5%. And the workloads for our evaluation are derived from the Facebook and the Bing traces. And we have a 150-node deployment. In terms of completion time, this graph plots the reduction in average completion time with respect to the two baselines that I mentioned, and plots this thing with respect by binning the jobs according to the number of tasks they contain. Clearly, we see that that the smaller jobs see a sizable fraction of the benefits here, but the larger jobs get some benefit as well when the cloning budget is available. Importantly, the slowest task now runs just a little a little slower than the median task in the job. Recall that this value is down from the 8x and the 6x value that I mentioned at the beginning of my talk. The key reason why we get this is because of the fact that we have delay assignment that balances out nicely between the two extreme options that we had, CAC that went for the exclusive copy and CC that went for the earliest copy. Clearly, our delay assignment is about 1.5 to 2 times better in terms of the gains it provides compared to these two extreme options. And the benefit of CAC only increases as the number of phases in the job grows. Typically, while the simplest map reduce technique has 2 phases, which is map and reduce, jobs could have a DAG that consists of many phases that could be pretty deep. This graph plots how the benefits compare with for the delay assignment, CAC and CC as the number of phases in the job increases. Not only are the benefits with delay assignment reasonably steady, but there's also a growing gap with respect to the other two delay extremes, which only emphasizes the value of picking this delay dynamically. So to conclude, what we've seen is that traditional mitigation, straggler mitigation strategies are not particularly suited for these small interactive jobs, which are growing in importance in these clusters. We had a proactive approach for cloning of these jobs and picking the earliest. And despite the fact that this is seemingly heavy-handed, we could get away with a very small cloning budget because of the heavy-tailed distribution that we see in job sizes. And our evaluation shows that Dolly actually provides nearly effective mitigation in terms of eliminating the stragglers. And as of now, we're working on trying to see if we can apply this thing of cloning to other scenarios where latency is pretty important and where a power law exists in job sizes. Thanks. Happy to take questions.
Christopher Stewart, Ohio State University. I really like your work. I especially like the intermediate comparison of CC to CAC that's neat on intermediate data. My question is about the former, on the input data. I'm wondering if you have any ideas about rigorous approaches to actually determine what is a small job in terms of number of tasks.
So one of the things we avoided having to do was to specify specifically which one is small, which one is large. And this was something I did briefly mention was when we said we have a cloning budget, what happens is when a job comes in, the job, if we require that, okay, if we say that it requires a specific number of clones, then we create it as long as there is available cloning budget that we have in our cluster. So by this, what we can do is avoid specifying, which one is a small job, which one isn't, and also utilize this budget for cloning even the slightly larger jobs as long as there is the cloning budget remaining.
Is there insight on how to set the budget correctly?
That would kind of be like some amount of sensitivity analysis. We have some of it in the paper, but the insight would be depending on how the knee in the power law actually is in that workload. Yeah.
Sanjay from Purdue. Actually, I'm just does this is there any case where cloning can backfire? Does this rely on the fact that stragglers are kind of random, correlations do not occur, or can there be some weird correlations that could sort of backfire the cloning algorithm?
One of the points at which the cloning will not be effective is something like, say, data skew in say, some of the reduce or the aggregate kind of tasks. Mm-hmm. If a task fundamentally has much more work to do than the other tasks in a job, then trying to create clones of it not only would be useless, but perhaps since these are the larger ones, they would end up taking way more resources and cloning budget as well. So that is something we are careful about in terms of how you go about doing it. Yeah. The fundamental assumption, of course, is the same as speculation, where that creating an extra copy is actually going to speed it up, and that these are actually independent in terms of how they function. But yeah, so the data skew is definitely one of the things where that assumption doesn't hold, and so we do not clone.
But I guess can there be correlations in data center failures, or a whole bunch of nodes all proving to be stragglers, or are these ever observed, or do these tend to be very random kinds of events?
As far as we've seen, it tends to be random, which is why things like speculations, etc., work.
Okay.
But what you're saying could be interesting in terms of trying to explore where, in terms of if you schedule these speculative copies itself, where would you want to place them? Like if a rack is particularly problematic, putting all of them together would get to a scenario like what you're mentioning in terms of correlations. So well, that's something that we haven't explored. I can imagine at least transient periods where something like that could occur.
Okay,
Yeah.
thank you.